Mr. Chao, thank you very much. I want to extend a warm welcome to all of you joining us today. On behalf of the Science History Institute, I wish to thank the Ting Sung and the Weifeng Chao Foundation for their generous support of the annual Chao Symposium. Today and in the future, the Chao Symposium will focus on sharing stories of creative thinking and new technologies in green chemistry, chemical innovations that address the pressing environmental sustainability challenges of our time. Our program today will present 4 sterling examples of innovative thinking in sustainable chemistry, with, as Mr. Chao said, a particular emphasis on water, shared by leaders in chemistry and in allied fields. The insights our presenters will share with us promise to resonate globally. Indeed, following this presentation, the program will be shared with a large global audience of researchers, entrepreneurs, and students of all ages via YouTube and through the Science History Institute's content sharing partnerships with schools and nonprofits across the world. Following our 4 featured talks today, I invite you to participate in a question and answer period with our presenters. As Christine just mentioned, please feel free to post your questions during the talks via the Zoom chat feature, and please enjoy the presentations. It is now my pleasure to introduce our first speaker, Dr. David Constable. Dr. Constable is the science director of the American Chemical Society's Green Chemistry Institute. In this role, he works to catalyze and enable the implementation of green chemistry and engineering throughout the global chemistry enterprise. David has held a variety of industry roles in energy, environment, safety, and health, focusing on influencing scientists, engineers, and decision makers who are responsible for chemical research, development, and manufacturing in the chemical, pharmaceutical, and aerospace and defense industries. He has developed a variety of programs, systems, tools, and methodologies that integrate sustainability, life cycle inventory and assessment, green chemistry, and green technology activities into existing business processes. His presentation today is entitled Opportunities and Challenges with Water in Sustainable Chemistry Innovations. Dr. Constable, welcome to you.
Thank you so much, David, for the very kind introduction, and it's a pleasure to be with you all today. Unlike Mr. Chao, my presentation is not going to be dealing with the petrochemical industry or large bulk commodity chemical production, but rather more along the lines of pharma and batch fine chemical operations. And it's really those opportunities in new molecule development that I'm going to be talking about. I'm indebted to Professor Bruce Lipschutz and Professor Sachin Honda for their seminal work in chemistry and water, and a variety of chemists in a number of pharma companies like Takeda, AbbVie, Merck, and others that are investigating chemistry and water. So next slide, please. Oops, that's me. A little bit about the Green Chemistry Institute. We're a small staff function, which is part of the ACS of the ACS. And we are basically trying to implement green sustainable chemistry in science and research, in education, and in industry. I can't talk about water apart from talking about solvents in general. And if you look at the pharma and the batch chemical operations, solvents account for the largest percentage of mass that gets processed. This has been known for quite some time, for almost 20 years. And basically, you get a distribution of solvents versus water in any kind of batch chemical operation. Solvents are just hugely important. More recently, with the addition of biologics, large molecules to the pharma sector, water has become extremely important. So whether you're talking about monoclonal antibodies or proteins or vaccines, the bulk of processing solvent that's used is water. And when it comes to solvents, whether it's water or an organic solvent, these are the kinds of things that one needs to think about. So inert reaction conditions. The reason that so much organic solvent is used in most batch chemical operations is largely in isolation, workup, and crystallization. And the same is going to be true for water. How we get the desired product out of water is quite a sticky problem. Solvent recovery and recycling, the ultimate treatment of those solvents is extremely important and contributes greatly to the cost profile of any chemical process in the batch process industries. Solvent guides have been around for quite some time, and actually, since 1998, the first solvent guide was published by GSK. And you can see that many of them, they sort of form this format where you're looking across solvent classes, and then you're looking at solvents from the perspective of green versus ones that you really want to avoid. The problem is in modern chemistry, in academia and in industry, is that water is not used too much. In academia, a lot of these solvents down here in the red corner are used routinely. And what we've been trying to do for many years is trying to get academia and industry to think about choosing solvents that are up here. So let me back up a little bit just to show you. This is the solvents counting for the greatest proportion of mass. This is the proportion of mass in the biologics area. This is a standard solvent selection guide, and this is where I'm at right now. So surfactants have been introduced largely by, I should back up and say that reactions in water have been done and shown. People like C.J. Lee over 20 years ago was routinely demonstrating a variety of reactions that could be done in water. The real innovation, though, that has enabled this to be more useful in modern chemistry has really been the use of surfactants. And this was based on the work of Bruce Lipschutz and Sachin Honda. And they developed a whole range of surfactants. The first one that really came to focus was this TPGS 750M. And like I said, they've developed a variety of ones. The most recent one is this PTS. But surfactants have been used for years, a variety of surfactants. What really makes these surfactants different is that they are degradable. They are non-toxic. So vitamin E analogs means that they don't have the usual toxicity characteristics of something like Triton X or some of the other surfactants that have been used in the chemical industry for years. The other thing has been development in these catalysts is that there are many solvents for common reactions, coupling reactions that have been produced over many years. But in order to make them work in water, you really need to make them much more lipophilic. And so that's why the vitamin E analog, or in this case, you have these large bulky molecules that have really been able to create these micelles in water. And it's in these micelles that all of the magic happens, if you will. So why do we want to use water as a solvent? Well, arguably, it's a green solvent. Doesn't have a lot of the baggage that other solvents do. I don't know why it's doing that. Sorry. Whoa. You'd think I'd never gave a PowerPoint presentation before. Sorry about that. It's a green solvent. There is the potential for direct isolation. There's mild conditions, potential for complementary reactivity. I'm going to talk a little bit about that, and you can do tandem biocatalysis. There are some cons to this, most notably about reaction workup and environmental impact. But basically, surfactants can be applied to a broad range of transformations. I'm not going to go into details about this, but these are common reactions that are used in bioactive molecule development. And the variety of catalysts are used. Unfortunately, a lot of platinum group metals, which the industry can't get away from just yet, but there is a lot of movement towards enzymes. Common reactions, I'm not going to go into the details of these, and I don't expect people to understand them, but the bottom line is that these are reactions that are very useful and important to industry, the pharma industry and agro industry. The neat thing about this is that this is done at room temperature and pressure, and most reductions are usually done at high pressures and high temperatures. Amidation reactions, so another important reaction class, cross-coupling reactions, the Suzuki's and Sonogashira type reactions. Again, all have been demonstrated. Another thing I'd like to point out is that the amount of metal, that catalyst that is being used, is typically much lower than what you will find in many organic solvent type reactions. And again, allows people to do tandem type reactions. What that means is that you don't have isolations and you can go directly from one reaction into the next reaction. You can also do sequences of chemo and biocatalytic reactions, just again, without any kind of isolation. And that makes the ultimate overall process much more efficient in terms of its mass intensity. I did mention about wastewater treatment, and that is very important. The neat thing about this is that these micelles can be extracted with solvent, or you can hydrolyze them. Ester groups are easily hydrolyzable with acid, so you can break them down and then directly discharge them. So it makes the treatment of water wastes from these kinds of reaction liquors very straightforward. So there are tremendous number of opportunities with this type of approach. There's surfactants as much or even less water than you would typically find in an organic solvent-based reaction system. Water waste is equivalent to traditional surfactant water. Organic solvents not entirely avoided, but generally you use less hazardous and much less solvent, and most of that solvent is just used for workup. Many times the surfactant water can just be filtered and dried, and you can get the product directly, so that's a great advantage. No new capital investment required, and basically the technology is driven by the physical properties of various components of the system. So again, this is a nascent field. It's one that is being vigorously investigated and lots happening. It really is a realistic option for chemists. It's a more sustainable alternative. So a big problem in the industry is dipolar A product solvents, things like DMF, DMAC, NMP, so on and so forth. These solvents can be avoided by this particular technology, which is a huge advantage. There's a lot of work, so the toolbox is growing and our understanding is growing. There are continuing developments in catalytic systems as well as reaction systems to enable this. And there's lots of new things to be discovered. So just a quick plug for our annual conference. We are going to be in Long Beach, California next June, and there will be several sessions on reactions in water chemistry. And I realize we're not going to do questions till later, so I'll stop sharing and pass it along to the next person. Thanks for your kind attention.
David, thanks so much. Much appreciated. It is now my pleasure to introduce our next presenter, Dr. David Kaniski, 2 Davids in a row. Dr. Kaniski's presentation today is entitled "The Next 50 Years of Water Quality Protection in the United States: Addressing Unmet Challenges. Let me tell you a bit about Dr. Kaniski. He is the Linton Caldwell Professor of Environmental Studies at the Paul H. O'Neill School of Public and Environmental Affairs at Indiana University, where his research and teaching focus on U.S. environmental policy and politics. His research has been published widely in leading environmental, public policy, and social science journals, and he has authored or edited 6 books, including 50 Years at the U.S. Environmental Protection Agency, Progress, Retrenchment, and Opportunities, and another title, Cheap and Clean, How Americans Think About Energy in the Age of Global Warming. Dr. Kaniski's research has been funded by the National Science Foundation, the U.S. Department of Energy, the Russell Sage Foundation, and the Alfred P. Sloan Foundation. He earned his PhD in political science from MIT, and he also holds master's degrees in environmental management and international relations from Yale University, and an undergraduate degree in history and environmental studies from Washington University in St. Louis. Dr. Kaniski, the floor is yours.
Great. Good afternoon, everybody. It's a real pleasure to be here. Thank you to the Chao family and their foundation for sponsoring this symposium, and to David for that very nice introduction. So I'm not a chemist, so this talk will be a little bit different, but I hope equally as compelling. What I hope to do in the next little bit here is talk a little bit about where we've been and where we're going with respect to managing water quality in the United States. And I think the place to start that is just to note that, we're now 50 years from enacting the U.S. Clean Water Act, right? And almost 50 years from putting in place the Safe Drinking Water Act. And many of you are probably familiar with these images, which are quite infamous, reflecting the Cuyahoga River outside of Cleveland that is sort of literally catching fire due to pollution loadings. Not the first time that this particular water resource had caught fire. What was so galvanizing about this was the attention that it brought to, on a national scale, to the challenges of pollution in our waterways. And it's no coincidence that just a few weeks ago, EPA Administrator Michael Regan revisited Cleveland and the Cuyahoga River when he came to celebrate the 50-year anniversary of the Clean Water Act. And one of the things he notes in his remarks was how much progress has been made. And I think that's a really important place to start, and that's where I wanted to sort of spend a few minutes, because we've made a lot of progress. And there are still areas from short challenges that remain, but it's really important as a starting point to note that a lot has been accomplished over the past half century. And I'll just share a few slides to sort of characterize some of those advances, some of those improvements that we've seen in the quality of our environment. So here are just some graphs from a nice paper by Kaiser Shapiro, which look at a variety of measures of sort of improvement in water quality. And some of these are actual compounds in waterways, others are designations of the quality of our surface water, looking at whether or not they're fishable or swimmable. And what you see pretty remarkably is that we're doing better, right? There's the declines all across the board by these metrics, right? All of which are indicators that we have been making pretty good progress on at least the quality of many of our surface waters. Just another measure, we can look at acidity in surface water quality. In this case, a lot of the improvements come from efforts to reduce sulfur dioxide that's being emitted from particularly Midwestern coal-fired power plants, and that was producing acid rain, which was leading to the acidification of ecosystems, lakes and forests and stuff, and particularly in the eastern part of the country. And the best we can measure, we've really improved by reducing sort of the acidity of those resources. On the drinking water side, in 1970, just a few years before we enacted the Safe Drinking Water Act in the United States, it was estimated that about 40% of the community water systems that were providing drinking water to people in our country were failing to meet basic standards, right? And now, if you look on the right side to the data the EPA makes available, we're now to a point where maybe 85, 90% of community water systems are meeting all the health-based standards that we've set. Now, of course, in this intervening period, we've added lots of contaminants of concern that have to be treated. So we are doing better, not just on a percentage basis, but we're actually treating and protecting our drinking water from many more compounds and contaminants. So those are all good news. That's all great. And I could probably spend the rest of my time talking about other indicators of progress. But I do want to highlight that there are still challenges that lie ahead. And from my perspective, the challenges are mostly not technical, but rather speak to sort of governance, resources, and politics. And by politics, I'm not talking about partisan politics, although certainly that's part of this as well, but thinking more about the large interests that we have that influence policy, shape the kinds of policies and programs that we have in place. Now, I want to talk about just 4 things. 4 challenges that remain. This is not intended as an exhaustive list. It's just four challenges that I think are particularly important for us to grapple with. The first being deciding what should be protected. Second, addressing the problem of non-point source pollution, particularly from agriculture. Third, dealing with both old and new contaminants. And fourth, addressing what are pretty significant disparities in outcomes. And I'll walk through each of these 4 things in just a few minutes. So first, what should be protected? As we sort of stand at the 50-year anniversary of the Clean Water Act, one thing that is really important to note is that there are some key ambiguities in the legislation that has complicated policy for a long time. And one of the things that's really ambiguous is that the Clean Water Act, Congress, when they wrote this legislation, never provided a clear definition for what is termed the waters of the United States. The way to think about this is what resources are supposed to be protected by the law itself. Because Congress was ambiguous in defining this term, it has left it to regulatory agencies to decide, whether it be the U.S. Environmental Protection Agency, the U.S. Army Corps of Engineers, and because of changing administrations, changing ideas, changing politics, these definitions have changed over time, and this has created considerable confusion and conditions for politics to win out over science, as I note here. To be more concrete, what this means is that over the history of the Clean Water Act, questions of whether tributaries, intermittent streams, isolated wetlands, whether or not they're protected by the law is not settled, right? It's determined on sort of a case-by-case basis, on an administration-by-administration basis, and it creates a lot of uncertainty. The courts are the place where this gets adjudicated, right? Not always by scientists, but by the courts. And in fact, just in the past month, the Supreme Court has once again heard another case, in this case, Sackett versus the US EPA, which they're going to tell us what counts as waters of the United States. And all this goes back to the fact that Congress has not been very, very clear. So just one illustration of where policy ambiguity creates confusion on the ground, and it's something that we still, 50 years out from the passage of the Clean Water Act, have to manage our way through. A second thing, addressing non-point source pollution. So the first thing to say is the Clean Water Act has been extremely effective in reducing pollution from quote unquote point sources. Think of wastewater discharges from a utility or from an industrial source. We have made great strides, and through technological gains and through other techniques of reducing the contaminants in the effluent from those kinds of facilities. But the Clean Water Act does not require meaningful action on non-point source pollution, right? So for those unfamiliar with that term, this is referring to pollution that is diffuse in origin, typically associated with wet weather. Think agricultural pollution in particular, although certainly not the only kind of non-point source pollution. And specifically, there's a lot of concern about nitrogen and phosphorus from agriculture. It is impossible to sort of not emphasize enough just how much of a problem this is. And it stems from the fact that the Clean Water Act does not explicitly mandate that we reduce this kind of pollution. In fact, many kinds of agriculture are exempted completely from the law. What are the implications of this? Many of you, I'm sure, are familiar with algal blooms that occur in some parts of the country with quite regularity. The picture on the left is of Lake Erie, where there's a summer algal bloom pretty much every year. In some circumstances, it is so bad that the water becomes toxic. And cities like Toledo have had occasions where they've been unable to provide drinking water to their citizens because the source water is so toxic. On the right-hand graph, these showing sort of trends in the application of phosphorus nitrogen, or I should say the measurement of these in national streams and rivers. And we see that despite having a pretty rigorous Clean Water Act in place during this time, we've had an increase in each of these kinds of pollutants. This information comes courtesy of Todd Royer, who's a colleague of mine at Indiana University. What does that all mean? Well, the best we can tell when we measure impairments of rivers, streams, lakes and ponds, bays and estuaries, you see that we're struggling to meet the standards of the Clean Water Act. In the cases of rivers and streams, lakes and ponds, more than half of the waters that are assessed are not meeting their designated uses, which means we're not quite meeting our expectations or the obligations of what the Clean Water Act has put forward for these water bodies. So in most cases, this is because of the non-point source pollution, particularly from agricultural sources. This is not particularly restricted to one region of the country. It's actually a problem throughout, to different degrees, of course, but the pollution and sort of the impairments that we see across the country is a pretty ubiquitous problem, which is to say water quality is a challenge for most parts of the country. Now, just one final point on here, we do have programs in the Clean Water Act which are intended to reduce non-point source pollution, but they're small and they typically don't require changes in behavior on the ground. And in aggregate, they don't provide enough resources, right? So one estimate, if you were to take the case of Indiana, where I live, you were to impose a program where you required cover crops, which is one strategy for reducing non-point source pollution. It's been estimated that might cost about $500 million per year in Indiana alone. We are currently spending somewhere in the order of $200 million nationally per year. So lots of work to be done on that front. Third, handling new and old contaminants. And this will just be an abbreviated set of slides because this is a much larger issue than I have time to discuss. Thinking about drinking water, right? EPA now regulates in the United States over 90 different contaminants in drinking water, right? These apply only to community water systems, which do serve about 85% of the population. They don't apply to private wells, and that's a whole other set of issues that we could think about. There are lots of pollutants, lots of contaminants that have to get regulated, right? And when I say old contaminants, I'm thinking of things like lead. And when I say new contaminants, I'm thinking of things like PFAS, right? There are others, but these are pretty good cases that reflect the fact that we're struggling with still contaminants that are, they've been around for a long time, and then more recent concerns like PFAS. So everyone's familiar with what happened in Flint with the lead water crisis there. And it's always important to highlight that, this is a problem that is manageable, and the creation of the problem in Flint was more about mismanagement and the lack of a strong governance structure. But Flint was not alone. It did bring an immense amount of national attention to this issue, but we see lead problems in other major cities in the United States. Newark is a good example. You can see some data here on the right, giving you a sense of just how many water samples are above the EPA threshold for being problematic. What you see in terms of lead levels in kids being much larger in Newark as opposed to other parts of New Jersey. Newark has undertaken a pretty extensive effort to replace lead service lines throughout the city. This highlights just how big a problem lead service lines are still in the United States. By this estimate, EPA has identified over 6 million lead service lines that are still in place. Of course, not all of these are causing lead contamination. They do signal the potential. This has been estimated to cost probably about $60 billion to replace. We have made a down payment on this through recent legislation, but still probably only getting us about a quarter of the way there. So more work to be done on that front as well. PFAS. Obviously, lots of attention in recent years are coming with PFAS. The extent of PFAS contamination across the country, I think, we're still in the early stages of understanding and learning about. According to this one study by the Waterkeeper Alliance, they found PFAS being pretty common in many waterways. And they found in their assessment of 114 waterways that 83% contained at least one PFAS compound. And in most cases, there are multiple compounds, right? So the EPA is still at the very early stages trying to figure out what to do with PFAS. We're likely to see a drinking water standard at some point in the coming years. We're also likely to see standards set for cleaning up contaminated areas, contaminated water resources that contain PFAS. And then finally, one last set of ideas to leave you with, thinking about disparities in outcomes. So the first thing to say is that by some measures, rates of noncompliance under both the Clean Water Act and the Safe Drinking Water Act are a little bit high. According to some recent data from the EPA, about 20% of major permit holders under the Clean Water Act were determined to be in significant non-compliance with their wastewater obligations, right? Progress has been made, this has been reduced, but it's still a pretty high level of non-compliance. In terms of drinking water systems, about 8% of community water systems were in violation with the health-based standard in 2021. What I want to note here and emphasize is that there are really some important disparities in non-compliance rates. And I just want to talk about two before I wrap up. The first thing to note is that many of the problems, many of the locations where water systems are struggling with compliance are smaller systems, particularly systems in rural low-income areas, but systems where there are only a few or small number of users, like in the hundreds or small thousands, as opposed to the big urban systems. And the reason is that it's expensive to meet all of the Safe Water Drinking Act requirements. And when you can't sort of spread those costs on a large user base, it becomes really challenging to raise the resources you need to meet those standards. Similarly, smaller systems struggle to bring in the people with the right technical know-how who actually can have the expertise to operate. And these things are thought to lead to higher rates of non-compliance. The second thing is there are some really important disparities based on race. People of color in both the Safe Drinking Water Act, as you're seeing in these slides from a paper by Switzer and Teodora, are more likely to live in areas where their systems are not meeting standards under the Safe Drinking Water Act, right? Stated a little bit differently, in places where more people of color are living, their systems are not able to sort of meet the standards with the same frequency. This same pattern of disparities is also true in the Clean Water Act, and this comes from studies that I and others have done. When you look at efforts by government to enforce these laws, you see that there are really important disparities. There's consistent evidence of both race and income-based disparities in regulatory enforcement of the Clean Water Act. So what I hope to sort of show through, or I guess one last slide, is that the solution to these problems is money, is investment, but not just money. It's also about governance. And for those of you paying attention to what's happening in Jackson, Mississippi, which I'm sure many of you are, the struggle in Jackson is not just about resources, it's about putting in the know-how and maintaining systems so they can provide safe and affordable drinking water to their citizens. So as I conclude, the last thing I'll say, just to remind you of the sort of the core argument here, is that the challenges are really not technical for the most part. They're about governance, resources, and politics. And they are solvable, but require us to sort of have some collective action and to take sort of the impetus to make progress on these fronts as well. Thank you. I appreciate your time and attention.
David, thank you so much. Much appreciated. And I'm now delighted to introduce our next presenter, Dr. Sherri Mason. Dr. Mason earned her bachelor's degree from the University of Texas at Austin. She completed her doctorate in chemistry at the University of Montana as a NASA Earth System Science Scholar. While a professor of chemistry at SUNY Fredonia, her research group was among the first to study the prevalence and impact of plastic pollution within freshwater ecosystems. Sherri has been featured in hundreds of mass media articles, including on the BBC, The Guardian, The New York Times, The Huffington Post, and on National Public Radio's All Things Considered and Studio A1. Her work has formed the basis for the Microbeads Free Water Act, which was signed into law by President Obama in December 2015. Similar legislation has been approved or is being considered at various locations internationally. Among her accolades, Dr. Mason has been awarded the EPA's Environmental Champion in 2016, Excellence in Environmental Research by the Earth Month Network in 2017, the Heinz Award in Public Policy in 2018, and the Great Lakes Leadership Award from the Great Lakes Protection Fund in 2021. Dr. Mason currently serves as the Director of Sustainability at Penn State Erie, the Barron College. Welcome, Dr. Mason.
Well, thank you so much for having me. I'm really enjoying this symposium. It's such a kind of a different assortment of speakers, and that's quite enjoyable. So I'm here today to, I study freshwater plastic pollution. And so I'm really going to be talking about kind of the paradox that is plastic. So plastic is a paradox because it's such a kind of a unique material. It has the strength that is equivalent or similar to what you would see in metals or ceramics, but is so much lighter than these materials. That makes it kind of really attractive from a material standpoint, adding to that the fact that it is so moldable, right? And I love the way that Susan Frankel used this in the title of her book, Plastics: A Toxic Love Story, showing various products that are made out of plastic, right? A chair, a comb, a lighter, a plastic bag, medicinal equipment, a bottle of water, and a Frisbee, really showing kind of the unique moldability of this material. The paradox, kind of the irony of this, is the fact that these same features that make it so attractive from an industrial standpoint make it a concern when it comes to the environment. Plastics are very lightweight, as we discussed, which means that they're easily carried through wind and through water, to end up covering different, all aspects of the globe. So we can go from the top of, Mount Everest to the bottom of the Marianas Trench, and we find plastics. It's also extremely durable, as we discussed. And the reason for that is really because plastics, unlike other natural materials, don't biodegrade. A paper bag sitting on the side of the road is certainly unsightly, but within weeks it has completely mineralized. But that doesn't happen with plastics. The polymer chains within plastics aren't really readily biodegradable. So instead, plastics undergo a process that's called photooxidative degradation, whereby they just break into ever smaller and smaller pieces, but the polymeric chains that make up the plastics, very little has happened with regard to their chemistry. Of course, plastics don't just become a nuisance at the end of their life. The ultimate starting material of plastics is fossil fuels. Within the United States, most of this refining occurs within the Gulf Coast of the United States, in an area that's referred to as Cancer Alley, because of the largely air emissions, to some extent water emissions, that come off of these facilities. And this is moving not just in the Gulf Coast, but is moving up to my area of the world, in Pennsylvania, because of hydrofracking, leading the Guardian to ask this question: will a push for plastics turn Appalachia into the next Cancer Alley? And it's because of the fact that hydrofracking leads to not just dry gas or methane, but also wet gas. And wet gas tends to be higher in ethane and propane, and so is not as attractive from the standpoint of energy production, but is really attractive when it comes to the manufacturing of plastics. This is an ethylene cracker plant in Beaver County, Pennsylvania, that at this point, when this picture was taken, was being built, but as of this past fall is now fully operational. It is the first facility within the Ohio River Valley, but two more sister facilities are planned for just over the border, further down the Ohio River, in Ohio. And what these facilities produce are these little pre-production plastic pellets, sometimes commonly referred to as nurdles. To give you an idea of size, this is me holding one found along one of the beaches here in Erie, along Lake Erie. So these pre-production plastic pellets are produced in these facilities. And that facility that I showed you a minute ago is currently in operation. These are some samples that we just recently pulled out of the Ohio River, just downstream from that facility. So the air emissions that come from these facilities, but also they end up inadvertently kind of releasing these pellets into the environment as well. So plastic, has an issue from the moment kind of it is born. It is also transported as these pellets largely through rail car and then through trucks. And to move them from one container to another, they are vacuumed out from one silo to another. And if anybody has ever disconnected their vacuum hose at home, you know what happens, that there's always, some pile of dirt that comes out. But in this case, it's piles of these little plastic pellets. These are images that I took underneath some trains on my way to work, actually, here in Erie, Pennsylvania. So these materials are, leading to emissions at their birth as they're transported and kind of as we go through the entire life cycle of plastic usage. Speaking of, over the 70 years that plastics have really kind of been a common part of the consumer culture, we've seen an exponential rise in these in the production of this material, to the point where in 2019, we produced over 465 million metric tons. And over the course of that 70 years, we've ended up producing a total of 10 billion metric tons of this material. To give you an idea of the scale, what that really looks like, it's the equivalent of 1 million Eiffel Towers or 100 million blue whales. And what has happened to all of this plastic, of that 10 billion metric tons, about a third of it is still in use, right? So you can think of, chairs in a classroom or your refrigerator or maybe your car. But that means that 70% of it has led to waste. 11% of it has been recycled, but more of it has actually been burned than has actually been recycled. And we still have the 75% that has been discarded. And current estimates currently put that of this, about 10 to 15% has ended up kind of being released into the environment, kind of forming some of those new pollutants that David was talking about just before I started speaking. As a topic of research, this really started in the world's oceans, but over the last decade, we've really realized that what is in the oceans is making its way through freshwater ecosystems. I happen to live on the largest freshwater ecosystem in the entire planet, the Laurentian Great Lakes. Over the last dozen years, I and some colleagues have been doing studies within the Great Lakes. And basically what we have found is that as we follow the flow of water, we see the increase in plastics along the surface of the lakes increasing, so that you get this additive effect as you move from, plastics moving through the systems, but then additional plastics being added as you move from lake to lake, ending with each lake containing somewhere between 1 billion pieces of plastic and 5 billion pieces of plastic just along the lake surface. Current estimates say that there are about 10,000 tons of plastic that get put into the Great Lakes Basin every year. 97% of these plastics are what are termed microplastics. That is that in their longest dimension, they are less than 5 millimeters in size. 75% of them are truly micro size, that is smaller than 1 millimeter in their longest dimension. Some of these are those primary microplastics, those pre-production plastic pellets that we made reference to earlier, but many of them are secondary microplastics, so things that formed from the breakdown of other plastic products. I'm going to flash forward to some of our more recent work showing where we looked at microplastics within common consumables. We looked within sea salt, we've looked in beer, we've looked in tap water, And as a consequence, actually, the tap water study, we did a global bottled water assessment as well. And what you see is that kind of no matter where you look, you find plastic. And when you're talking about a product that is packaged in plastic, the amount of plastic that you find is exponentially higher. In fact, this is a review article where authors were able to account for only 15% of the average American diet. And found, that this is, if you've ever heard the statistic, that you're eating about a credit card's worth of plastic every day. It's from studies like this one, with bottled water being your kind of biggest release of microplastics into your diet. So to kind of add to this, are these microplastics making their way into people? We found them in our feces. Really interesting study done by a colleague of mine, looking at the placental boundary, finding microplastics on both sides of the placental boundary, both the maternal and the fetal side. In fact, babies having more microplastics than adults. This was a match study, so pairing a parent with the child and looking across those. Just recently this year, it's conclusively been found in human blood and within the deepest lungs of our deepest tissues of our lungs. So there is kind of really no doubt that microplastics are making their way into us and becoming kind of one of those new pollution problems. In terms of solutions, I often refer to this idea of this overflowing bathtub or an overflowing sink. What are you going to do if you come home and see this? And the first kind of innate assumption is you're going to turn off the tap. And I think that is really where the solutions focus, is finding ways to regulate and decrease our usage of this material. It's an incredibly unique material, but its prominence is mostly within single-use packaging. That represents 50% of the market. And so there are ways that we can regulate this in order to push the market in ways that we want it to go. So it's been reintroduced into Congress for a second time, the Break Free from Plastic Pollution Act, which really is about shifting marketplace so that one, the onus of recycling is not borne by taxpayers, but rather instead by the industries who are using this material, and then shifting the markets to push industries to use plastics that are easier to recycle, to use less variety of plastics, and to find ways to reduce single use when possible. And so with that, I want to thank you for your time, and I look forward to our questions at the end.
Many thanks for your presentation, Dr. Mason. And now I'd like to introduce our final presenter, Dr. Julie Zimmerman. Dr. Zimmerman is an internationally recognized engineer whose work is focused on advancing innovations in sustainable technologies. Dr. Zimmerman holds joint appointments as a professor in the Department of Chemical and Environmental Engineering and in the School of the Environment at Yale University, where she also serves as the Senior Associate Dean for Academic Affairs, as well as the Deputy Director of the Center for Green Chemistry and Green Engineering. Julie also serves as the Editor-in-Chief of Environmental Science and Technology, the most highly cited journal in environmental sciences and engineering. Her work is focused on the innovation of products and processes in academia and industry, including her own research group that focuses on topics including breakthroughs to convert biomass into chemicals and fuels, design safer chemicals and nanomaterials, work on sustainable water treatment, and perform analyses of the water energy nexus. Professor Zimmerman is the co-author of the textbook Environmental Engineering: Fundamentals, Sustainability, Design, that is used in the engineering programs at leading universities domestically and abroad. She earned her BS from the University of Virginia and her PhD from the University of Michigan, jointly from the School of Engineering and the School of Natural Resources and Environment. The title of her presentation today is Designing a Green Chemistry Future. Dr. Zimmerman, we are all ears. Thanks.
Great. Thank you so much for that introduction. So I'm going to start off with a photograph. So this is a picture of a tanker car driving through Washington, D.C. You can see the Capitol building in the background. It looks like a pretty old picture, but this still happens 3 times a week in Washington, because this tanker car full of chlorine gas is heading to the Blue Plains drinking water treatment plant. For those of you who are familiar with chlorine gas, it was first patented in the early 1900s as a chemical warfare agent. So we have to step back and ask ourselves, is this really the best way that we can go about in providing clean, safe drinking water to the residents of Washington, D.C.? This tanker car full of a chemical warfare agent, subject to potential accidents, sabotage, vulnerability to terrorism. And this isn't just happening in Washington, D.C. This happens in many urban centers around the world as we meet the important goal of providing safe drinking water. So the problem with this is, and the problem with this example is emblematic of many of the challenges of how we try to address sustainability challenges like providing clean drinking waters, that we're often playing whack-a-mole. And we know we have to provide safe water, but we wind up using toxic chemicals to do this. We want to address our climate challenges. And it turns out when we go after things like corn-based ethanol for fuel, we disrupt biodiversity and we wind up putting more energy into the system than we get back out. So I'm an engineer. I've been trained as an engineer all through. I teach engineering at Yale. And I would say that, you know, this is basically what we've been taught. There's a problem, you come up with a great idea, and you have a solution. And this has been applied and demonstrated across many aspects of society, whether it's transportation, water and wastewater treatment, healthcare, communications, on and on. There's just one problem with this. We have been solving the wrong problem, or at least half the problem. So for example, somebody said, we need to provide clean water, but they forgot to tell us that we need to do it without using and generating toxic chemicals. Or we want to generate energy, but we should do that without altering the Earth's atmosphere or produce goods and services, but let's do it without depleting finite resources and generating waste. And you could go on for all of the sustainability challenges we're facing in terms of meeting societal needs. So the solutions that we come up with, we want to make sure meet societal needs in ways that are conducive to life today and into the future. And so we really need to not solve just the first half of those problem statements. This really requires changing the inherent nature of the materials and energy sources that underpin our society and our economy. And we think about this going back to some work done by the National Academies in 2014, where we started to say, okay, what is it about these chemicals, these materials that we're producing that lead to challenges and problems in their environmental fate, and then ultimately in their toxicity? So if we're going to change the nature of the materials and energy sources we're using, we really need to think about it from a molecular basis. And so this is really the molecular basis of sustainability. We think about this often using a biomimetic approach. So lots of great examples from nature about how we can solve our problems. And if we boil all of it down from how Mother Nature addresses this, we want to move to solutions that are renewable and not depleting, healthful and not toxic, and restorative and not degrading. And if we just add that to those first few problem statements about providing water, about producing enough food, about generating energy, we'd go a long way to addressing many of our sustainability challenges. So if we want to get the problem statement right, it's the same way we get the solutions right. And that is really by coupling reductionism, which is how we tend to do science, with systems thinking. And there was this really brilliant paper published by Paul Anderson in 1972, who went on to win the Nobel Prize. And he wrote this paper called More is Different. And it really goes on to talk about how using reductionist hypotheses does not imply a constructionist one. And that is, if we reduce everything to very simple fundamental laws, it doesn't mean we can reconstruct the universe. And so we have spent a lot of time doing science and trying to understand how things behave in isolated environments, but not in actual systems. And this has led to a lot of these unintended consequences, like using chlorine gas to treat drinking water. So if we think about systems thinking, this is a really good example. I'm sure glad the hole isn't in my end of the boat because we're all in this together. And so tools of systems thinking would say that we want to start thinking about how things are interconnected. And I'll talk about the water energy nexus in a minute and how we can learn some lessons there in solving it. We want to think in circular systems, and I'll talk about how the chemical enterprise needs to move from a linear system to a more circular system. How to allow and understand emergent behavior in systems, how to understand how things work together, how to do synthesis rather than just analysis, and how to understand relationships. So we know that water and energy are quite inextricably linked. We know from lots of work that's gone on that water use and energy consumption continue to increase, and that the rate at which they're being consumed is also increasing. We also know that energy and water are very closely linked in that it takes a lot of water to produce energy, whether it's for fracking, as we just heard about, it's for cooling towers on coal power plants, it's for mining to get coal out of the ground. And we know there's a lot of energy embedded in the water that we use, whether it's for pumping, for treatment, for distribution. And so the state of California had set some pretty audacious energy goals, and that they wanted to reduce the amount of carbon that was coming off their grid. First, it was 40%, and then it was 100% by 2050. And they started to spend money in the past decade or so on upgrading the energy grid. So this included introducing renewables, solar and wind. It included some energy efficiency work in terms of transmission lines. It had to do some with demand side management and managing energy consumptions around the smart grid and what people were using in their homes. And you can see they spent about 22 to 28 cents per kilowatt hour on reducing these tons of carbon from the electricity grid. And we did an analysis and said, hey, if instead of focusing on energy, and we understand that water and energy are linked, what if we went after water use efficiency goals rather than just thinking about energy savings from the energy side, from the electricity grid? And it turned out by doing things like reducing the amount of evaporation out of water treatment plants and reservoirs, by addressing leakages, by putting in low flow toilets and shower heads, and spending money on water use efficiency, we could realize their carbon goals for about 12 cents a kilowatt hour instead of the 22 to 28 cents they were spending. So this saved them around 50% in terms of the relative cost of reducing carbon by addressing our climate goals through water rather than through energy. And of course, as California continues to face a drought, there are co-benefits of thinking in these interconnected systems, because I'm also addressing some water scarcity concerns at the same time that I'm seeing carbon and climate benefits. So if we want to get where we're going and solving these problems in a sustainable way, we want to couple reductionism with systems thinking, as I just showed in that water energy example. We want to couple innovation with sustainability. We want to couple discovery with development, and we want to make sure that we can implement things at scale. Science in 2020 did a series of issues on science for tomorrow's Earth, and one of them was dedicated to chemistry. And I, along with some co-authors, were invited to write the perspective on designing for a green chemistry future. And we, in that paper, really laid out the challenges with today's chemical sector being quite linear, relying on fossil feedstocks, relying on really reactive chemistry, using catalysts that are based on rare earth elements, Lots of waste that's generated, as we heard, from solvents, relying on waste treatment, really focusing on the use phase and designing for function without having a lot of consideration for the other half of the problem statement in terms of hazards and sustainability, and why we need to move to tomorrow's chemical sector that looks much more circular, relies on renewable feedstocks and benign chemical agents. And in this paper, we also laid out a flow chart of how do I go about doing this if I'm really interested in pursuing sustainable solutions. So if you think about the first thing you have to do, whatever you're designing, it has to do what it's intended to do. If it's a dye, it has to be the right color. If it's adhesive, it has to be sticky. So I want to make sure whatever I'm doing is providing the function it's intended to do. The second thing to think about is it being made from depleting resources? And if it is, can I redesign it to utilize renewable feedstocks? Lots of the work that we do at Yale thinks about these questions of how do I take biomass and mimicking a petroleum refinery in something like an integrated biorefinery, how do I cover value from every fraction? Just like a barrel of crude oil doesn't just produce gasoline, but we get kerosene and naphtha and biodiesel and heating oil out of it. How do I think about a biorefinery in the same way, whether it's algae or lignins or cellulosics or waste plastic, as we heard about, or even food waste? Based on this idea and some technologies we've developed, we've spun out a company called P2 Science that's based up here in Connecticut that uses vegetable oils to produce sustainable flavors and fragrances. And they're manufacturing at scale now and supplying to companies that you're all quite familiar with, like Chanel and L'Oreal and Unilever. So now that I have my thing that I've designed that does what it's supposed to do, and I can make it out of renewable resources, the next thing I want to do is make sure it's not toxic. So as we go back to the old understanding of risk as a function of hazard and exposure, we've done a lot of work at our center to develop guidelines and software tools to think through how do I know if what I'm making is going to be toxic or not as I develop new green chemistry innovations. And so thinking about chemical properties, things that we know are likely to be toxic, things that tend to bioaccumulate, and can I come up with design guidelines that ensure that the things I'm making don't look and act like the things we know that are toxic today. And then the last thing gets into this question of, do I design for degradation? So is it something like a shampoo or a pharmaceutical that I'm never going to get back into a circular economy, and I want to make sure I design for this to degrade safely into the environment? Or is it something that I do hope enters a circular economy and recycle and reuse loops, in which case I want to design for persistence? When we think about this end of life, we're really interested in thinking about how do we recover value from waste. And another company I'm really excited that we spun out of our center is called Air Company. Their first product that went to market was vodka, pretty high-end luxury product. So this is taking CO2 and sunlight and water, electrocatalytically splitting that water to make hydrogen, reacting it with the CO2 and producing ethanol. Vodka was a great product to start with because you can sell it for about $80 a liter as opposed to about $3 or $4 a gallon at the gas pump. During COVID, they shut down production of their vodka product and did produce hand sanitizer for first responders in New York City. I'm happy to say they're back at their vodka production. But the other thing that they've worked on is now gotten a $20 million grant from NASA to thinking about how do we take CO2 out of the atmosphere, whether it's here on Earth or as NASA thinks about colonizing other places, and turning that into sustainable rocket fuel or other critical feedstock materials like glucose. So Air Company has now demonstrated they can make glucose from CO2 and water. And they also have started producing sustainable aviation fuels. We now have offtake contracts from Virgin Atlantic and JetBlue, as well as the United States Air Force. And I'm going to show a quick video here.
there's supposed to be sound. So these guys are pretty amazing at marketing, as you can tell, but also really excited that we have the first carbon neutral, sustainable aviation fuel on the market today. We heard the other speakers talk about the issues of environmental justice. This is something really important to think about as we go forward and thinking about the historic and egregious, really, disparities in terms of disproportionately disadvantaging communities that live at the fence line of chemical plants. So I make a joke in my class when I put up this picture, I say, can you point out the chemical plant in this picture? So these fence line communities are often low income, immigrant communities, people of color. And so it's become very clear over the work of the past 50 years, and particularly of Robert Bullard, to demonstrate and quantify and characterize these environmental injustices that are happening. So when we think about green chemistry, in contrast, I'm putting up a picture here of the Brooklyn Navy Yard, which is where Air Company is based. And if I ask you to point out where the chemical plant is in this picture, you can't find it. And in fact, there are restaurants and bars and stores located in the same place that we're producing that sustainable aviation fuel. This changes a lot. It changes the concept of NIMBY, of not in my backyard, of not wanting chemical companies to come in, to saying, I'm excited to have a chemical company come in. It helps my tax base. It creates opportunities. It creates jobs. And I don't have to trade off or pay with my physical health, my mental health, my well-being, in order to have access to those opportunities. So I'm going to wrap up really quickly here. So I've talked a lot about green chemistry, which is really the science and technology of what we think about in terms of a sustainable future and the innovations where they need to happen. But it's important to remember in our analogy here of the periodic table that not only do we need the science and technology, but we need those enabling systems conditions, the economics, the market forces, the policies and regulations that we heard a lot about, the tools in terms of knowing what to regulate and how to regulate it, and the metrics in which to quantify if we're making progress towards our noble goals. And so I'm going to end here. The difference between what we do and what we're capable of doing when more than suffice to solve most of the world's problems. And so I'm quite optimistic about the opportunities we have in front of us. And I'm happy to stick around and answer any questions.
Terrific. Many thanks, Dr. Zimmerman. Appreciate your talk. And again, my thanks to all of our presenters today for introducing us to the challenges and also, I think, the opportunities presented by sustainable chemical research as it relates to innovations around water, all from their different fields and subfields and different perspectives. As we mentioned, our four presenters have agreed to take questions, and we've got a couple. And one is initially directed at Dr. Kaniski, but I wonder if it might, in fact, be appropriate for all four of you to take a crack at this one. You mentioned, Dr. Kaniski, in your talk, this problem we have with small systems non-compliance, basically small communities where there's insufficient ability to attract investment, not a big enough opportunity to scale solutions that makes them, unattractive for a variety of reasons for the kind of innovations that are needed to address the contamination of water. I'm wondering if you, or for that matter, I'll open up to the other three of you, if anyone can point to experiments taking place, case studies, experiments in particular communities where you see a glimmer of hope, where you're excited by what's being tried and that potentially a solution in that small community could eventually be scalable other places.
Well, I tend to think about the idea of solutions broadly, right? So I'm sure there are innovations and technology and such that maybe other speakers can speak to, but we can also think about changing the systems themselves, right? So there's a big movement towards consolidation, right? To thinking about how to pull, rather than having systems provided by small communities, but try to pull those resources into larger systems. It isn't always true that bigger is better, but in the case of water systems, often it is. There are economies of scale. There are ways to harness better human capital. And I think we're seeing sort of innovations in the sort of the policy space and in the markets to have that kind of happen, right? So that's kind of one solution that is becoming more frequently talked about, and you do see examples of this sort of taking hold. Now that's challenging because people want ownership, they want control, they want autonomy, and it's kind of cutting against that. But that is one kind of policy innovation and sort of market innovation that we're seeing tried across the country.
So I'll just jump in. As far as small scale, it's almost the opposite of what you just said. There's a lot of work, particularly being funded through the Superfund program, to think about distributed small scale, even at the household level, new technologies, particularly understanding membrane technologies and the cost of those coming down so significantly, as well as using nanomaterials to nano-enable different water treatment, like your Brita filter, so that it removes some of these new contaminants that we're worried about, as well as the historic ones, and making those filters much smarter in terms of telling the consumer when to change them based on that, not the time that's passed, but either how much water has flowed through or actually how much of the capacity to remove these contaminants has been consumed already. I think the other place we see really great small scale solutions is in the global south and in communities where we don't have infrastructure right now. And so how do you provide safe, clean drinking water on demand in places that don't historically have access? And there's been a lot of work on appropriate technologies that work and make sense in those communities based on their culture of whether it's pottery and ceramic filters, or in the case of India, there's been a lot of work to bring community scale reverse osmosis membrane systems in. And so I think you're seeing really innovations across the marketplace for these smaller scale and household systems.
Yeah, and in fact, I think those, you mentioned a couple of areas where I think the Gates Foundation has gotten involved with some additional investment, particularly in Africa, where we may see the fruits of that in the next 5 or 10 years. And this one is more particular, and it's for David Constable. And it says, can you actually name some companies, whether they're mature companies or perhaps development stage companies that are pursuing innovations with surfactants and water that you were describing? Are there folks looking at this as a commercial opportunity, either large scale or very early stage development stage, that have attracted your attention?
Absolutely. So I'm sorry that wasn't clear from my talk, but the company that's most in doing this and really demonstrating it at scale is Novartis. But virtually, well, not all, but many of the very large pharma companies are investigating this and using it on a regular basis. We just last week were talking about a life cycle assessment of and a route to a molecule that's done in organic solvents and water, and that's a key question. So I think there are also contract manufacturing organizations like it's PHC, I think it is, that is their whole business model is based on using the surfactant chemistry. So yeah, it is being used already. The one thing to answer that last question about scale, one of the things that Julie was talking about is looking at things from a systems perspective and looking at things, a distributed means of delivering a function. And what I would say about that is that in my mind is certainly the future, but we have to be really careful to evaluate those technology solutions from a life cycle and a systems perspective, because many of them look good at small scale or even at distributed, but they don't. The overall resources in both energy and materials is far greater to actually implement it at a large enough scale across, Earth scale. And so I just would provide that as a caution about small scale solutions.
Well, speaking of scalability, let's shift gears for a second. And another question here, and this has more to do with your role as educators. And at least part of your lives, all four of you have in common that you have served or serve as educators. In a sense, you've been playing that role today in your presentations, teaching us things we didn't know. And I'm wondering, in your capacities as educators, have you imagined or in fact even implemented curricular changes or other education, or have you seen or participated in other educational innovations that you think could be useful in informing and perhaps even inspiring the learning public? There's a question about you have a lot of information to share. There's a question about how do you get that information out there in a compelling way? And I'm wondering whether in the classroom proper or in other educational settings, you have either thought about or actually tried new approaches to the educational process around these water issues that you think are effective and inspiring. You get to put your teacher hats on for a second.
I can't speak to water, but what I can say is that we've been actively approaching a reform of curriculum for general and organic chemistry to try and implement systems thinking, green and sustainable chemistry within the context of the Sustainable Development Goals. This is enormously challenging because the way chemistry and chemical engineering have been taught really hasn't changed in 60 or 70 years. Mm-hmm. Fundamentals of how they're taught at most universities. And to teach it from this perspective is enormously challenging because educators aren't prepared or equipped to teach it that way. And in developing educational resources, many of them don't have the exposure to how things are made at an industrial level. So they teach things that work at a laboratory scale, but you could never use within industry. So yes, we're doing it. It's an enormous challenge, but it's going to take some time to do it and complete it.
Other thoughts from the pedagogical or curricular side? Sherri?
Sure, yeah. I think for me, because I've stepped from being a chemist to being the director of sustainability at the Erie campus of Penn State. And so what it really did was kind of shift my mind. I realized that a lot of the way that we teach is about how we're not sustainable. But we are a society that is monkey see, monkey do. And so if we are always teaching about how we are not sustainable, then we are not going to become sustainable, right? And so shifting more to showing examples of sustainability and which is kind of, I appreciated all of the people I got to serve on this panelist with, although I felt like I was the odd duck, but all of you were really talking more about, kind of alternate ways. And so you're more talking about what sustainability is, what, doing things in the right way looks like. And that's what you need in order to kind of shift and turn the boat in a different direction. And so I think that that's kind of the vantage point when I approach. So I teach classes where I'm going through all of the sustainable development goals and one a week. And so as we're going through those, I'm thinking, how do I switch this instead of just telling them all the doom and gloom about how, we're not meeting, and instead shifting it so that you're, so when I teach about, like, for example, sustainable production and consumption, I give the students examples of things that are not sustainable, and then I ask them to redesign it, with the secret being that they all have sustainable options out there. And so trying to get them to realize that there are options out there. It's just more about, as kind of David pointed out, David Kaniski, it's not about technology, it's about policy. It's about kind of shifting perspectives, so that we're pushing our society in that direction.
Julie, you had a comment too, I think. I'm sorry.
Yeah, I mean, so we've done everything from develop new curricular materials to developing games, designing safer chemicals to try to make it more accessible. We work a lot through science fairs and coming up with science fair projects. And then I teach a class at Yale with Paul and Astis on sustainable innovation. So we have a makerspace here on campus with 3D printers and laser cutters, and we bring in corporate clients who have sustainability challenges. And the students actually have to come up with a product innovation in a semester. And the final exam for that class is basically the TV show Shark Tank. So they have 15 minutes to pitch their product. And we have local VCs, as well as the companies that sponsored the projects in the class. And so I think it's, as Sherri was saying, it's giving them the power of what's possible, and it's letting them go through the innovation process. And it's, you know, it's interesting because students who come to Yale have always kind of been taught the right answer. And when we say there is no right answer, and we say, you know, if you're going to pass this class, you have to fail, because if you haven't failed in what you're doing, you haven't really pushed the envelope, you haven't tried something new, you haven't really innovated. And it's really getting students to shift that mindset of there is a process, everyone can learn innovation, and that you can do this in 3-4 month semester and come up with something really creative and exciting. And we've seen students go on and take that to startup companies and small businesses that they created out of those ideas.
So a little bit of the business school wrapped into the chemistry class, or vice versa, cross-disciplinary thinking, which seems to be where we're all headed, I think, in a positive way. This is a more narrowly tailored question. This one is for David Kaniski. You talked about non-point source pollution, which I think is something that is largely in the public vocabulary. It has been for some time. We've been hearing about non-point source pollution as a big problem for a long time, for decades. That's been in the air. What are the prospects that Congress or government agencies or other legislative bodies will take steps around non-point source pollution in the near future?
It's a great question. It's an important one, and at the risk of being some of that doom and gloom that we were just referring to, I mean, I think this is a huge challenge, right? And one of the things we were talking about, how we teach things, how we talk about these issues with our students, and one of the things I always point out to my students when I'm teaching about the Clean Water Act is that the issue of non-point source pollution was not unknown at the time, right? It's not that we didn't appreciate the extent of the problem or realize the extent to which it was going to continue to be a problem if we didn't make a different set of decisions. It was a choice that we made not to regulate it. So we've continued to make that choice for a number of years, right? And it's striking that we have the environmental laws that we still rely on in the United States are the ones that have been around for many decades. So I don't know if the prospects are great, at least at the national level, but you do see quite a bit of experimentation and innovation happening subnationally, locally, at the state level. So there are some serious efforts, not necessarily to change the behavior or the incentives of farmers, but to give them opportunities to invest in things like cover crops and other kinds of interventions that may make a difference. So, I don't see great prospects for a new regulatory regime, right? But I think we're seeing sort of a change at the federal level in other areas like climate, where we're trying to create new incentives for people to make better choices. That's sort of slow. It's not it's sort of fragmented, but I think that's probably the best opportunity for change is to create more opportunities and perhaps subsidizing or providing better incentives for farmers to do things differently. That's kind of where we are as I see it. It's a tough problem, but the impaired waters that we see are largely due to non-point source pollution. So if we don't make better choices, when you see how it's being exacerbated by climate change and other factors, we have to make a different choice. And just back to your last question, what I tell my students all the time is that the world we have, the planet we're living in, this is our choice. We're making choices, and to try to empower them to make different choices than what my generation has made, what my parents' generation has made. And that, I think, is uplifting to students, right? To sort of have them understand that the future is in their hands, right? And they have to sort of embrace it and help us create sort of innovative solutions to get us out of these problems.
So speaking of inspiring, I get to ask one more question, but it's a big one, and it's to all of you, and it's inspired in part by what you and Sherri and Julie were saying about different approaches you've taken with students to get them excited, focusing on opportunities and chances to innovate and create, as opposed to simply the gloom and doom. And I'm wondering, we heard a little bit about exciting things happening on the spectrum, everywhere from jet fuel to vodka. I'm wondering if I asked each of you, if you could point to one innovation, whether it's a technological innovation or it's in the realm of public policy, government's approach to these problems. If you could point to one innovation where the prospects excite you in the near term, what would that be? Perhaps something that hasn't already been mentioned in your 4 presentations collectively, but one innovation that you'd like to leave us with that would excite or inspire us. What might that be?
For me, it's the prospect of synthetic biology. And that basically is molecular engineering and using a variety of platforms, molecular organisms, small organisms as chemical platforms, and really transforming. It was already mentioned, the fact that we're dependent upon petrochemicals, and we need to figure out a way around that, the chemical industry. And to me, that is the future, is employing whatever microorganism to make the chemicals we need.
Julie, I think you had a hand up, perhaps.
Yeah, I was struggling a bit when you taking CO2 and making chemicals and fuels and materials out of it. I think that is one of the big things we need to figure out how to do. And I think from a policy perspective, I think one of the biggest things we could do is move from regulating chemical by chemical to more property-based regulations, so that we start regulating classes of compounds, like PFAS is starting to be considered, so that we're not always kind of chasing the next least bad thing on the shelf, but we can actually say to chemical designers, this is safe operating space if you follow these property guidelines. I think it will support innovation. It'll speed up the process very much, and we'll have much safer chemicals and materials as a result.
I can jump in next.
Good.
Sherri, another moment to think, perhaps. What has really excited me sort of in the policy space over in recent years is the fact that we're beginning to make connections across policy spaces, and particularly around environment, energy, climate, water. The intersection with social justice has become undeniable and part of the public discourse in a way that is really different than it has at least existed in recent decades. And I think policy will follow slowly, but that recognition, I think, sort of forces us to think about the nature of these problems a little bit differently, whether it's affordability, whether it's pollution burdens, whether it's access to new technologies. And I think that new conversation is really exciting. I think it's here to stay. And I think it's forcing everybody to confront the fact that this disparities we have are really significant and need to be front and center as we're making decisions about public policy. So I'm really excited that we're having that conversation. I think it will lead us to new places and new policies and programs.
Thanks.
Yeah.
Sure.
I like that point that David just made, which, I think I mentioned in my talk the Break Free from Plastic Pollution Act, which obviously I mentioned it because I'm pretty excited about it. And I think it connects to that point. And it connects to, I mean, what I'm really excited about is that I feel like there's a lot more conversation going on about circular economies and finding ways to be, this kind of realization that we've built a society based on this linear kind of thinking that Julie made reference to. And that doesn't work on a planet, right? With limited resources. And so, there has to be, and so there's a lot more conversations going on around circularity of this economy, circularity of that, ideas around, instead of buying light bulbs, renting them. And then there's incentives for the light bulbs to be made to last a very long time, as opposed to, the current incentives, which is for them to die quickly so that you buy a new one, and, so it's using the market and using regulations and policies to shift the market to end up with the results that we want, right? We want clean water, we want this. How do we use regulations to turn the ship in the direction that we're trying to lead to? And I do think that is encompassed in the Break Free from Plastic Pollution Act, where it's like, if you're going to use a plastic like polyethylene that's easy to recycle, then you don't have to pay the overhead as compared to using something like a polystyrene that is kind of very near to difficult to impossible to recycle, and kind of, so you're using the market to shift society in the direction that you want it to go. And the whole conversation around circularity, that's what I'm really excited about.
Well, I'm excited about all the proceeding, and I want to thank you all. I think you get the last word there, Sherri, but really all four of you have, I think, helped us catalyze a conversation that at Science History Institute we want to continue. We want to continue it globally around the intersection of sustainable theory, practice, and water, our most precious resource. So I'm sure the conversation will only continue as we promulgate our programs far and wide. And in fact, as I mentioned earlier, today's program will be made available shortly to a global audience via YouTube and to school audiences, because Science History Institute, again, has partnered with educational and cultural institutions around the world to share our content for free, always free. We encourage you, all of you in the audience, to share it among your friends and your colleagues. And as always, to follow more of what we call the stories behind the science that we like to tell at Science History Institute by engaging with us at sciencehistory.org. That concludes our program. Many thanks again to our presenters. Many thanks to all of you for joining us. See you next time.